Okay, again, good morning to all of you. Are you ready are we ready to start?
Yes, sir. I think we can start.
Okay, okay. Okay, I hope my screen is visible and voice is clear. So, yes, good. So far, we have discussed in detail about the forward layer of the diffusion model. So we have discussed in detail that how we systematically get the noisy image from the original image. So now it's time to discuss about the reverse process. And one thing that I'm again repeating that in the forward diffusion model, we are not using any neural network or any trained machine learning model. Uh, we are just adding the noise with some linear equation step by step and making the noisy image which cannot be recognized using the original image. Now let us see how we can just get back the original image from the noisy image. And the target is not to get back the same image that we have given as an input. Rather, we have to train the model in such a way that it should be able to generate the images or text or audio or video, whatever the data we are training for, uh, which is close to the real one. So we have to make our model robust enough so that it is after the training, it is able to generate the data with itself, and the data should be close enough to the real one. That means it should follow the similar kind of probability distribution as the original data is. Now let us see the reverse process in detail, and we have already discussed that diffusion process works in two phase, forward and reverse. And in the reverse process, definitely we are going to use some neural network model, some deep neural network model, which have enough capability to predict the noise that we have added in the each step, and that's our ultimate goal. And now we'll check that what should be the actual loss function and how a model is going to be trained in order to get the original image that we have given near to the original image. Basically, reverse process is called as the denoising process that we have already discussed, and this is the main. You can say this is the critical part, or this is the most crucial part of the model, because this is the time when we need to a neural network, a deep neural network, which have the ability to predict noise that we have added. So this is the most, you can say, that the crucial or critical part of the diffusion models. The success of the diffusion model is going to depend upon the training of the neural network that you have used in the back propagation. So more better will be the performance of the prediction for the neural network that you are using in the reverse process. Better will be the quality of image that you are generating, or better will be the quality of any video, image, or text data or audio it may be generating, which will be close to the real one. Definitely, the goal is to reverse the forward diffusion process. Whatever we have done in the forward diffusion process, my ultimate goal is to reverse And for reversing, we are not using any statistical kind of methods. Rather, we are using deep convolutional network, which have ability to predict, and we want to automate this task so that we can just have the realistic images in future. And definitely in after the end of this reverse process, I will also show you um, some of the videos and images that has been generated by some companies like Google. It is really difficult to just predict and or classify nowadays that whether that particular image or video has been generated by AI or generated by humans. So again it is a new area of research that we should have some kind of models which can really bifurcate between the real and machine generated data or AI generated data. And definitely more is the advancement taking place in the area of generative AI, more it is becoming difficult to have some model which can classify between the AI generated and the real content. So we will also discuss in detail with that for that problem. Definitely, the first process that we have discussed is actually adds the noise in the data, and the reverse process basically learns. I haven't used this term learning in the forward process, but in the reverse process, I am using this term that is called learn, because we don't have to do any kind of learning in the forward process. So far, no doubt in future you can have your own uh, new kind of model. You can also use some machine learning or machine intelligence in the forward process as well. So that's a future area of research. But so far, we are not learning any kind of pattern in the forward process. We are just statistically increasing the noise in an incremental way in the forward process, whereas in the backward process, I am learning means I'm training the model based on some of the inputs or labels that we will give to the model. Okay, and naturally at the end of the reverse process, the model generates a clean data from the pure noise that we have given. No doubt this noise is pure, but this noise has been created by destructing the original image and adding the random generated noise in a Gaussian way. So definitely, reverse process is the just reverse of the forward process. That what we have done in the forward process, we have performed noising, and in the reverse process, we are just denoising it. So naturally, it is just reverse of that process. And the main problem, the main uh, task that we have to perform in the reverse process is to model p theta x of t minus 1 slash xt in such a way that I am able to, my model is able to predict. This is theta, means this is a parameterized model having some weights and biases. And what will be the role of this parameterized model? What whether it is a unit, whether it is a deep convolutional network, what kind of model it is, that will depend upon your problem and data. But my ultimate aim is to have a trained model which can predict the image or which can predict the data in the previous state. Given x of t, we need to predict the data in the previous state. So that will be ultimate goal. So that you can say that we need to find the probability for recovering x of t minus 1. So I need to go from x of t to x of t minus 1, and for this we need to know quantity of noise. What we need to do, we need to know the quantity of noise, that is a1 or beta 1 or whatever it is, that we have added in this step. So if you are able to know the quantity of noise, then we can just predict the image in this one. So x of t minus 1 naturally will be x of t minus alpha 1, you can say, where alpha is 1 is the quantity of noise that we have added in x of t minus 1. So we need to predict this one. We need to have a model which can do this. So this is the reverse process, and this is the equation of the reverse process. What we need to do, we need to know a model, we need to train a model such that p of theta is equivalent to x of t minus 1 slash x of t. That means given xt, I need to predict x of t minus 1, where in the case of forward processing, what we were doing, we were getting x of t by adding some noise in x of t minus 1 plus noise. So I hope that this object is quite clear to all of you, that what is my goal. This is the equation for reverse modeling, for the reverse process. This is the equation for the reverse process. And what is the meaning of each and every term? This is the image x of t minus 1 in the previous step. What is my requirement? Given xt, I need to find x of t minus 1. And how can I do it? How can I get it? I can get it by predicting this one. So what is this? Mu of theta, x of t comma t. This is the mean of the predicted clean data at timestamp t. At timestamp t. And no doubt this is the covariance matrix. At this moment of time, I am just which represents the variance at time step. So what we can do at each step, we can have some different variance in the noise, but we are keeping this constant. We are not changing it. So in future, again, I'm saying that you may have some kind of complex problems where you may just change the value of this variance by the course of iterations. But at this moment of time, I'm keeping this fixed one. Got it. So again, I'm telling this is the main equation where this is mu of this is basically the mean of predicted clean data. And this mu theta t that we have written in this previous equation, this can be typically modeled as in terms of alpha. So what is alpha? Alpha t is actually 1 minus beta t that we have already discussed, where beta t, if beta t is the noise, then alpha t you can say that it is the actual data. So it is also written here, that is alpha t is equal to 1 minus beta t. It is reverse of beta t. Again, this is a covariance matrix. So I think we are now clear with this equation. What is my objective? That I'm telling you again. I need to predict, I need to train a model which can actually predict the quantity of noise that we have added in the previous iterations. And by predicting the quantity of noise that we have added in the previous iterations, we can retrieve the image or actual data in the previous iteration. That is my ultimate goal. And if you are able to predict t minus 1, then I will predict x of t minus 2, then I will predict x of t minus 3, then I will predict x of t minus 4, and so on. By doing this, we can predict x of 0, that is the original image, not original, rather near to original image. We can say that we can generate an image which is close to the original one. This is the covariance process image that I am actually keeping it constant. No doubt you can see that this is a constant, or this is an identity matrix. Why it is identity matrix? If you are taking image data, then we have to multiply this with some identity matrix, so that we can have we can just map this according to the dimensions of the image. Yes. So what is the image at x of t minus 1? What is the image at x of t minus 1? This will be equal to the clean data plus noise. This is the predicted clean data that you have predicted, and this is the quantity of noise that you have added. Both are predicted. These are not the actual one. Got it? So basically, if you want to predict the clean data, that means you need to predict the noise. So naturally, x of t minus 1 is the clean data plus noise. My ultimate target is to predict this noise so that we can have the prediction of the clean data. Got it. So I think that we are clear so far. This is the same equation that we have written in different way. No doubt, x of t minus 1 we can say is equal to uh, x of, you can say that x of t minus noise, or in a more mathematical way, if we are writing, then this will be x of t minus 1b is the mean distribution of the original data, predicted data distribution, that is of noise. And naturally, if we'll keep on decreasing it, this is x of t minus 1, and by getting x of t minus 1, what we will do, we will get x of t minus 2. X of t minus 2 is equal to mu of theta x of t minus 1 comma t minus 1 plus e theta of x of t minus 1 comma t. And by doing so, we'll keep on reducing it. And if we'll come in the backward direction, ultimately at final step, that is called t equal to 0, the model will be able to generate x of naught. X of naught. Someone is asking, it will not be clean data, it will be noise. Which one? Which one are you talking? Okay, if you are confused, okay, if you are talking about in previous slide, means this one. So this is actually according to the model, this is predicted clean data for the previous step. This will not be the actual predicted clean data. But for me, for example, I am at x of t. I am predicting at x of t minus 1. So no doubt x of t minus 1 is not the clean data, it is noisy one. But at this time stamp, this is my clean data because I am reducing some noise from this one. Because I'm not predicting at x of naught, I'm predicting at x of t minus 1. So for me at this moment of time, this is clean and this is noise. And for x of t minus 1, x of t minus 2 is the predicted clean data plus some noise factor that I have added. Got it. And no doubt, if I will come at this step, x of naught, so this will be predicted clean data for me. X of naught, my ultimate is goal is to get x of naught. So no doubt, in the second last step, where we are going to stop, I will say to the client that yeah, this is the actual predicted clean data. So it actually it is a matter of timestamp that for which timestamp I am talking about. Got it. Okay, now coming to the original objective function, that what I need to optimize. That means what is the loss function that I need to know. So loss function, if you remember that if you don't want to go into the details of the mathematical terms that we are using, the loss function is quite clear that we have discussed in the starting. What should be the loss function? Loss function should be, for example, I am iterating 10 times, like t is equal to 1, comma 2, comma 3, comma 4, or comma 5. For example, I am iterating for the 5 times. At fifth iteration, for example, in this fourth to fifth transition, I have added noise like 0.5. In this, I have added, I'm just arbitrarily quoting some numbers. These are not the actual one. Just I'm throwing some numbers to understand the concept. At this point, the noise was 0.4. Here, the noise was 0.3. Here, the noise was 0.2 that I have added. Just assume. And what I need to know, I need to train a model which should be able to predict the quantity of noise that we have added. For example, my model have predicted that you have the noise that has been added by at this step is 0.5 0.49. That means my model is close to the noise that has been actually added. I have both the things. What actual noise that we have added, I have stored somewhere, and what is my model that is predicting. So, for example, this is the difference of 0.01. Again, in this step, I'm coming one iteration back. Here, my model has predicted 0.38. So, there is a difference of 0.02. Again, I'm coming back. For example, my model has predicted this as 0.27. So that means there is a difference of 0.03. In each iteration, we will have some loss. Why so? Because in each iteration, my model is predicting that what is the value of noise that that has been added at any given time stamp, that is called x of t. So in each iteration, while the reverse process, my model is going to predict that this is the amount of noise that might has been added. So that's why I'm just trying to make you clear that this is the instance that I'm predicting that at this moment of this noise is added, and this is the model that is predicting. And for example, here model is predicting 0.9, and this is loss of 0.01. So whatever the difference is between the true value and between the predicted value, that is no doubt the loss that I'm getting. And no doubt, why we calculate the loss? More will be the loss. That means my model will be needing to change the values of weights and biases. So this is only called the training. What is called training in the case of deep learning model? Training is just the process of tuning the value of parameters in such a way that the predicted output from my model will be very close to the near one. That is just called training, that we are already aware of. So what will be the actual loss? Actual loss will be the sum of losses that have been occurred at all the iterations. So what we need to do, we need to perform sigma. Sigma of 0.01 plus 0.02 plus 0.03 plus 0.01. And this summation is going to be the loss for that particular iteration. That particular iterations of the sum of the losses of all the iterations. Okay, so same thing that has been written here. The objective of the reverse denoising process is to learn the parameters, that is theta. Theta is actually the parameter that we are saying. M theta means model parameterized by the theta. And parameters are nothing but the weights and biases. And we need to know the value of parameters. No. Is my voice breaking or I'm not audible at all? Clear. Okay. Might be possible breaking a bit. Okay. So ultimately, ultimately what I was trying to say is that in the reverse denoising process, I need I need to tune, I need to learn theta. Theta means L of theta. Theta means the set of parameters. Set of parameters means weights and biases. Such that whatever the noise that my model will predict will be very close to the actual noise. What I need to do? I need to minimize the difference between the predicted clean data and actual data across all timestamps. If we have added the noise in 1000 timestamps, I need to perform sigma of predicted noise that has been added at every timestamp. So no doubt, it is also not fixed that which loss function you are going to use. But here in this case, because this is a regression kind of approach, so the most common objective or the loss function is the variational lower bound on the likelihood. This is written like this. Got it? So what is this? This is the difference between actual and predicted. What is this ET? ET is the noise that we have added in the each step in the forward process. E of t is the noise, is the actual noise that has been added in the forward process. For example, if I am talking about the fourth iteration, E of 4 is the amount of is the quantity of noise that I have added in the fourth iteration. And what is this? This is the predicted one. This is the predicted one. So basically, this is the difference between the actual and predicted. What I need to do. And what is this? This is sigma. Sigma from t equal to 1 to capital T, where capital T is the number of iterations that we have used for adding the noise in the forward process. So I hope that this loss function is quite clear to you. This is very simple and straightforward, and I am talking about this from the very beginning, from the first slide. That what is my main objective? This is my main objective. I need to train a model. I need to train a model, or I need to train a neural network which can optimize this. My target is to minimize this. I need to minimize this loss. Lesser will be the value, lesser will be the loss, and my prediction will be more close to the real one. Okay. What is the intuition of the reverse process? Naturally, that we have already discussed. Start from the pure noise. Forward process start with the original data, and convert the data to the pure noise. And what reverse process does? Starts from the pure noise and came back to the data which is near to the original data. At each step, the model predicts the clean data, that is xt of minus 1, from noisy, that is x of t, essentially denoising data. So prediction of the clean data is near equal to prediction of the noise. If I am able to predict the noise, then I can predict the clean data by removing the noise from that noisy data. Again, clean data x of t minus 1 is not the actual data that I want. This is the clean data at a particular timestamp t minus 1. And this predicted noise basically helps us recover the clean data by guiding the denoising process. Over the t steps, the model transforms random noise into high quality and meaningful data. This is my ultimate objective. Let us again visualize this. That how we are uh, uh, recovering the original image or near to the original image from the pure noise which has been created by destructing the original image. So this is my diffusion model exactly. What input this diffusion model is getting in the very first iteration t is equal to 1, what it is getting? It is getting pure noise. And what this diffusion model is doing? This is converting this pure noise or more noisy image to the less noisy image. And one thing I have also written in comment, that notice that output of the model is entire noise. No doubt this is also entire noise, but this noise is in somewhat less scale. I have reduced some noise from this one, but ultimately we are in the very beginning phase. So no doubt the output image will also be looking like a noise. So after, for example, we are running through 1000 epochs, so might be possible after 800 or after 700 epochs, we will be able to see the image features. Until 1000 epochs, we will be able to see the clear image. Got it? So again, this is also written in this box that the letter scale based on the schedule to be subtracted from the input. Whatever the noise my model is predicting, this is subtracting from this one noise. So in the initial stage, what I am getting a little bit less noisy image from the more noisy image by reducing some predicted noise. Okay. So again, the output from timestamp t, the output from timestamp t will become input for the timestamp t minus 1. This is quite clear. So for example, in the fifth iteration, my reverse process has predicted this image. Now it will become input for the upcoming iterations. In the next iteration, again what my model is going to do, it is going to predict some noise, and it is going to subtract this noise from this one to get the new image. This is the same equation that we have discussed earlier, but it is written in the form of alpha, and alpha t is equal to 1 minus beta t. Again, the generated image is the entire noise once again. Why it is so? Because we are in the initial stage of the reverse process. So whatever the noise we have predicted in this image, we have subtracted from this image, and we have got some less noisy image. At this moment of time, I am still getting a noisy image as an output, because we are the very start process of the reversing or denoising. Again, whatever image I will get as an output in the previous iteration will become as an input in the for the next iteration. How I have got this image? I have got this image by subtracting some noise from this image. For example, noise is n1. So this image is this one, x1. So this image is actually x1 minus n1. The result of denoising. Still, this is not a clear image. Again, this entire noise. Again, we are getting the same kind of image. We are still not able to retrieve the features, because also might be possible. You remember the point that what I did, we have a very small value of beta in the initial stage, but in the later stage we were keep on increasing the value of beta. That means in the later iterations of the forward process, we have added more noise. So in the reverse process, it is also going to take some time to start retrieving the features, because in the later on stages we have added more noise because beta increases. Yes, this is the reason we are getting entire noise one side. Again, still I am going one step ahead, but still I am getting noise. Why I am showing these steps again and again? In order to make a clear cut intuition in your mind that whenever you are going to run the code, so for example, you are running the code for 1000 epochs, so might be possible till 500 or 600 epochs you are getting pure noisy image. So you have to be patient, that it is going to take some time to start retrieving the features. Then after you will see that slowly you will start retrieving some of the information or some of the features in the image, and that image is going to be enhanced by the course of iterations again and again. But this time you can see that this image have some visibility. It is pure noise, but still, if I compare this image with this image, it seems that it has little less noise. It seems that. Again, okay. Now, just if you remember the input image, just look at here. Look at this image and this image. I'm just circling this point. You are able to see, might be possible you are able to see some hut kind of structures there behind this noise. That means whatever the steps I am showing to you are helpful in understanding or visualizing that how we are denoising the original image. Now it has some clarity. Yes, now it has some clarity. Whatever the output image is there, it has some clarity. So again I'm telling, this output image, this output image will become input for the next iteration of model. What my diffusion model is predicting. What is this? This is the noise. This is the noise that my diffusion model is predicting. And what I am doing here, I am reducing, I am subtracting. This is the clear cut step. Are you getting this one? This is the input image. This is the input image. This is the noise that my model is predicting. And this is the output image of this instance. How I am getting the output image? By subtracting. If this is x, this is y, then what I am doing? I am doing x minus y. I am just getting this image after subtracting the input image and this predicted noise. Can anyone just confirm me? Are you getting this figure clearly? How I am getting this output image? This is the noise that my model has predicted. The main objective of my diffusion model was to predict the quantity of noise that has been added in the previous iteration. So my model is doing the same. This is predicting this, that this is the noise that you have added in this image. My model is predicting that this is the noise that you have added in the previous step. So I am subtracting the same in order to get the image in the previous step. Can anyone just comment and just confirm me that you are getting this step? Okay, I hope that you are getting. Moving ahead. Again, my diffusion model is predicting the noise. Again, we are subtracting the noise from the input image. This is input image and this is predicted noise. This is the output image. This is the output image. Again, input, predicted noise, output image. This output image is going to become input for the next iteration. Again, my model is going to predict noise. Yes. So this is the final image that my model has created. So this is not the actual image. Rather, this is image which is near to actual image. which is close to the actual image that has been given as an input to the model. So now I think we are clear with the forward and backward process, how the diffusion model is able to do the job for us. Now the main thing is that what is the main or crucial part is to train a neural network model which can predict the noise, that has been added in the previous step. So diffusion model means the main backbone behind the diffusion model is the neural network that is predicting the noise that has been added in the previous step. Exactly. Now the question is, what should be the structure of that neural network? So let us see that what should be the structure of that neural network that will be best suited to predict the noise that has been added in the previous step. So again, I am not forcing you to choose this kind of neural network. You can have your own choice, but this is the basic kind of architecture, and this is the architecture that is similar to unit architecture. This is called unit. Basically, it is having U kind of shape. Goes downward, comes upward. Goes downward to basically downsample. So basically, this unit kind of architecture works in two phases. One is the downsampling phase, downsample, and one is the upsample. One is the downsample and one is the upsample. So you can just see the architecture, and I have also mentioned that which kind of blocks these are. You can just check the color combinations. So these pink blocks are the convolution block. Wherever you are seeing the pink blocks, just assume that these are the convolution block, and this color basically represents the downsample block. This green color represents the upsample block, and this color represents the self-attention block, and this is emptying vector. Depending upon your requirement, you can just have the architecture of your own type. So why this unit architecture is generally used? Generally, I'm not enforcing that this is the only architecture that you can use, but in the main paper that has been introduced, that has introduced diffusion model, the authors have used unit architecture, and they have defined that basically uh, this architecture actually better suits the process of noising and denoising. That's why we are using this unit architecture. You can try your own. Moreover, what you can do, you can have some kind of rather than using straightforward unit. This is some of the recommendations that I am giving on the basis of some of the implementations that we have performed. I will also show the code, and I will also give you the code which has been used for the generation of video images. So it is not the straightforward rule that you have to go for this kind of approach only. I'm just suggesting you. In the model that we have used for the generation of read images, we have used some skip connections from here to here. And what is the role of skip connections? Basically, if you see that in the unit approach or while noising the image, might be possible if your model have n number of layers, and what we are doing, we are downsampling it. We are downsampling the data. If you're downsampling the data, that means at each steps you are losing some information. Naturally, you are using some neurons in the each step. So might be possible at this moment while upsampling, you have lost a lot of information. So what you can do, you can just use some these connections, provide some information that has been lost to the upsampling layers. So that while upsampling, it may have some information from the background layers, and that may help model from retrieving the data, from retrieving the original data that has been lost. And again, for providing the information, you can use this sinusoidal embedding, and you can just go in literature. You can just check the number of permutations and combinations that can be used for retrieving the information. So that's up to you. That's again an area of research. I'm just suggesting you that you can just use this modified UNet architecture. But again, it is not mandatory that you have to use the same architecture that I'm telling you. You can just, I will provide you the code. You can just try different permutations and combinations to use the model. Now, again, I'm summarizing the overall diffusion process. On the data that we have done, we have performed the test on the wheat data. I'm just summarizing the overall process on this wheat data, that how the original images will look like, and how the reverse process will take place in order to retrieve the original images. And I will also provide the code for the same. So this is the pure noise images, and we have to start the reverse process from this point only. You can see. So these are the images after epoch 0 that we have done. These are the images after epoch 50. These are the original generated image from the code that I will give you. You can just match the results by running the code that I will provide you. These are the images that we have generated after 50 epochs, and the data is of wheat images. So you can have a number of real-time applications where you can use this basically diffusion model. So one of the major application in the research is the image augmentation. If you want to augment image, if you want to increase the number of samples for the minority classes, you can just use this kind of generative architectures. So this is the result after 100 epochs. After 100 epochs, you are able to see some of the plant-like structures hidden in the noise. This is some plant kind of structure hidden in the noise, but not the actual kind of or expected kind of images. But yes, somewhat after 150. We are now able to see clear cut how the images will look like. So these are some kind of plants. You can assume that this is a wheat data or some kind of plant data, whatever it is. 200, more clarity, less noise. 50, even more clear images. Yes, even more, even more. After 400 epochs, see the quality of images that has been generated by the diffusion model. Yes, 500, and so on. So now you can just visualize, you can just think of that what is the use of diffusion models that you can for your research purpose. There are a number of applications. For example, we have to just classify weed and crop, but you have less number of images for the weed, number of images for the wheat. What you can do, you can have your own diffusion model which can generate images like this. Now, might be possible diffusion model will generate images. You are saying 2 small plants here, and the model that will generate will have 3 small plants here, because it mimics the probability distribution of the data. So we can use this diffusion model for the image augmentation. You can use this diffusion model in the medical image analysis for making the image more clearer. You can use these diffusion models to generate fake scenes for a number of purposes in a positive way. Again, I will show you some of the videos as well that has been created by the diffusion model, and really you will not be able to bifurcate that. Yeah, these are looking quite original, that has been captured by some camera. This is the power of diffusion models nowadays, and still research is going on. Now, someone has also asked me that can you tell me the difference between the generative adversarial network and the diffusion models? Basically, I have also discussed some of the differences between the GANs and diffusion models. Basically, GAN starts with pure noise that has been created randomly, and diffusion model start with the noise that has been created by corrupting original image. GANs have generally, if I talk about the vanilla GAN, so GANs have got generally 2 neural networks. One is G and one is D, whereas diffusion model needs one neural network that is used in the reverse process. That is denoising stage. So the basic, in terms of idea, here GANs have generator and discriminator that compete in a game-like structure. Generator creates the data, discriminator tries to distinguish the data. In case of diffusion model, here a sample is gradually noised. Sample is gradually noised in the forward process. Then model learns to reverse this process and to generate the new data. Here I have already told there are 2 networks. One is generator G and one is discriminator D. Here usually we have a single network, and generally we take unit, and this is not mandatory. So far, it has been empirically validated that by performing a lot of experiments that UNet suits much to this one because of its architecture in U shape, and whereas we also do the same way noising and denoising in U shape, similar kind of structure. But this is not the mathematical evidence. This is just empirically validated. Here the training objective is min-max game that we have already discussed. Here the training objective is denoising the score matching, likelihood based. Score matching means actual noise. This. Achha, one more thing. The problem with the GAN was that one of the basic problem with the generative adversarial network was stucking into the local optima, because that function was multi-objective. Generator was trying to minimize and discriminator was trying to maximize. Something like this. But here in the case, the objective is not multi-objective. Here we have to just minimize the noise. So the chances of, no doubt, this diffusion model is compute intensive. This diffusion model is compute intensive because we have to do a lot of predictions here. In one iteration, we have to perform 1,000 times of predictions. But really it doesn't stuck into the local optima because my function is unimodal. We have to minimize this noise. So we don't have the problems like stucking into the local optima or just something like that we have discussed in the GAN models, mod collapse kind of problems. So here, what is output style here? They in the case of GAN, direct image is generated in one pass. Here in the image is generated in iterative refinements. So no doubt more computations are involved that have already discussed. So I hope now you have some clear-cut differences in the generative adversarial network and diffusion models. Now, at the last, I would like to discuss some of the challenges that diffusion models may have in a similar way that I have discussed for the GAN models, such as mod collapse and Nash equilibrium problem. So similarly, the diffusion models have the problems like slow generation, because in one step we have to do a lot of predictions in the reverse process. Here we need high GPU uses, long training time, and I think that you do now know that why diffusion models need high GPU uses, because in each epoch we have to perform thousands of predictions, and the loss is the sum of the losses of noise in each iteration. So we need a lot of computations. That's why high GPU usage is required. So in the case of GANs, we can have some conditional inputs like CGAN, condition based GAN. We can also provide some labels that you have to produce the image in such a way. But in the case of diffusion models, it is basically hard to do. So there are some challenges. So main challenge with the diffusion models is that its training required a lot of computational power. That is the main challenge for the GAN models. So I think from theoretical point of view, and from knowing the structure of the diffusion models and how diffusion models works in the backend, what is the main idea of the GAN models? You are basically aware with that. If you have any doubts or any questions uh, for the diffusion model, you can just ask me. Otherwise, I will just go through you with some of the audio and video generation tools, and thereafter I will discuss a diffusion based code to just show you. And I hope I should start with the code, and after that I will just make you aware with some of the audio and video generation models that are available in the literature. So all of you just open the Kaggle notebook. I am just giving you one link. Is my screen visible to all of you? Can anyone confirm me? Okay, okay. So just I have given one link, just click it. And again, what you need to do, you need to open this notebook, and I will provide this code to you so that you can just do some hands-on in. And here I will just discuss in a very quick fashion about what this code is doing and how we can just change the this code in order to generate the model as per our requirement. So you have to just click on it, and the right hand side you have to you will get a link to edit my own copy. Just click on that to edit your own copy. And moreover, one more thing, if your internet option is not on, just do it. Otherwise you will not be able to get the access of the GPU. So please check that in the right hand side, your internet is on or not. Okay, this session has started from my side. I have got the access of GPU. So basically, in the right hand side, you can see that these are the data sets on which you can just run. This is the flower data set. This is the sorghum data set. You can add your own data set to just work on. So these are basically some of the packages that I have imported. So basically, what I told you, the only uh, thing that you need to do is you have to just choose a neural network that will be used for prediction of the noise in the reverse phase. So what I have did, I have taken a attention based unit architecture. So I have added some attention blocks to the unit architecture, to the original unit architecture, in order to retrieve uh, basically lost information. So it's up to you which kind of neural network model that you want to use for your predictions. So these steps that you can just explore. If you have any doubt in any of the syntax, you can just copy it and paste it in the GPT. It is going to tell you about the functionality of the function, that which parameter this function is taking and which output this particular function is giving to you. And moreover, in the next session, you will also get some of the hands-on uh, with Satyen sir. He will just give you some hands-on with some of the more codes uh, for the diffusion and generative based models. Okay, getting the data set, you need to load the data set. I'm running cell one by one so that I can have the output, so that you can just visualize that how these diffusion models basically work. Data loader. This is just for visualizing. Batch size basically 128. That will tell you that in how many batches you want to train. This is just used to perform parallel processing, because I have the GPU access on the Kaggle. This is basically to show the images. I have shown 120. I have taken 128 images and 12 cross 6. This is the figure size. So this is basically the input data that you can see. I have just plotted the input data. I'm working on the sorghum data set at this moment. This is the original data. And now we'll start the diffusion process. So this is the number of epochs. I have taken 1,000 epochs. It's up to you that how many epochs you want to take. This is again the alpha and beta that we have discussed. So no doubt the alpha and beta will be required at the definitions of the algorithms. So basically, alpha is 1 minus beta, that represents the data, and beta represents the noise. So this is the beta start and beta end. I have already told you. The start of the beta I have also taken as 0.02, and end of the beta is 0.0001. That I have told you. Got it now? So basically, this is also a question of research, that how you are choosing the value of starting value of beta and ending value of beta, and how you are changing the value of beta with the course of iterations. So this is basically the forward diffusion process that you can see in the code. This is the forward diffusion process. I am just adding the mean and standard deviation. Yeah, this is basically the timestamps on which I am just showing you the images. It's up to you. So it is recommended that you should just print in between the outputs, that how your image is being generated, so that you can just visualize that how your model is denoising the image in order to get the original one. So I have printed in epoch number 0, epoch number 10, 50, 150, 200, 300, so that I can just see the intermediate outputs. Yeah, you can just see. This is the same thing that I have shown you, similar images. At timestamp t equal to 0, the image was like this. And in the forward diffusion, this is the forward diffusion process. At timestamp 1000, the image is looking like this. So you can see that uh, uh, if we are running through 500, 1000 iterations, after 200 iterations, the image is getting invisible. And till 1000 iterations, the image is pure noise. That you can check. This is the intermediate output of the forward process. Now I'm training it. For the training, what I have told you, I am using model that is called unit. And I have applied some attention blocks to the unit model. So that is attention based unit network. Why attention blocks are being used? In order to save some meaningful information in the intermediate layers. Also, you can make some video kind of things to just show to just check the intermediate process. So in this, what I did, I have created these image samples of 1000 epochs. Then I have made a video by combining those frames in order to just click on video and just check that how the image is converted from noise to required image. So for the forward process, I haven't created the video. That's why I have written false. But for the reverse process, I will make it true in order to make the video. I will also show you the video that I have generated. Now training one epoch. So in each training, this is the predicted noise and this is the loss. Loss is nothing but original noise and predicted noise. What this get noise function is doing, get noise function is getting the value of noise from the forward diffusion process. During the forward diffusion, what I have already discussed you in the very beginning of the session, during the forward diffusion process, I used to save the quantity of noise that I have added in each iteration, so that I can provide the ground truth value of the noise or actual value of the noise in the backward process. Again, this is the optimizer which is going to just optimize it. Now this is the process of reverse diffusion in the code. You can just do any, if you have any problem in the syntax of the code, you can just, I am again saying, you can just copy and paste it in the GPT. It is going to tell you that what is the input and what is the output and what is the actual meaning of this particular syntax, because there are thousands of lines, so I cannot dictate each and every line at this moment, but I am just going you the giving you the overview of the code, so that you can just do the modifications as and when required by yourself. So this is the reverse diffusion process. Again, I'm taking timestamp as 1000 and this is the image save. Going ahead. These are some of the steps that I have commented because I have tried a lot of permutations and combinations during the process. Generate video. Here, I have generated video for the reverse process. During the forward process, my generate video was false because I was not interested in that. But for the reverse process, I have generated a video that I can show you. This is the sampling. These are some of the combinations that I have commented because these are the repeated steps. also the training is already done. So if I will show you the results of the code, you can just see. I will show you how it had actually worked. The results of diffusion model. Yes, you can see the images. This is noise, noise, noise. I have printed this for the reverse process. Check. Noise, 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 noise. Again, in this, after some epochs, you will be able to see that the quantity of noise is being reduced. So now you can see that some features of image are now visible. Now see, after 900 iterations, we are able to see the features of the actual data. This is the plant that I am able to see. Just check. Now, moreover, these images are of less dimensions, 32 cross 32. That's why these images are not much visible. So, because if you will increase the dimensions, then the computation time is going to increase, but the quality will increase. So if you are making images of 128 cross 128, in that case your this Kaggle GPU is going to take, I think, almost 12 to 14 hours of training, but no doubt you will be able to see quite good quality images. But in this I have just used 32 cross 32 images uh, in order to convert this fast. So I have got the results in, I think, 20 to 25 minutes, but that are not quite clear, but we can see that these are the images. Now, if I have also generated a video that you can see, I will show you the video of the reverse process, not the forward one. Inference result. Just see how these are the noisy images. You can just reduce the frame ratio, frame convergence ratio. You can just reduce the speed of this video in order to see it more clearly. Just see, and see. In the later stage, you will be able to see that this noise is getting converted to image. The level of noise is being reduced by the course of iterations, yes. And in the last stage, yeah, yes. Just see, features are arriving, and yes. Basically, what I told you in this particular code run, I have used image dimensions as 32 cross 32. But if you will increase the dimensions of the image, that is 128 cross 128 or some more dimension images, then you will be able to see clear cut images. Okay, I hope uh, you have got the intuition of the diffusion model in detail, that how this diffusion model work. I'm going to share you the notebook with you so that you can run in future. So let us coming to some more applications of this diffusion model and generative AI. That is how we can generate basically video. So video is basically, you can just think of is an extension of the image. If you are creating the frames, and if you are running the frames 16 frames per second, then it is converted to video. So if you are able to create images, then naturally we are able to create videos, but as a matter of fact, we will be needing more computational power. I'm showing you some videos. Just This video is basically generated using VO3 that has been developed by Google. I am also showing you one more video. Have you seen this video? So have you seen this video? This video is actually not a real video, rather it is a video which has been generated by AI. Now you can see the power of generative AI nowadays. This video was looking very, very real. But as a matter of fact, this video was generated by AI. So similarly, not only video, we can also have generation of audio by mimicking the pattern in the same way that we have did it for the image, that we did for the text. So nowadays, AI-based models such as Google's Music LM, these are being used for the music creation. For the synthesis, you know, majority of the news channels nowadays, what they are doing, they are doing AI anchor this one or that one. So AI anchors, those anchors are able to just process the data from the web, and they are able to convert that text into the voice, and they are able to read news for you. So this is the power of generative AI in the field of audio systems as well. Sound designs. So basically, what we do 10 or 5 to 10 years back or 15 years back, we used to listen for the AR Rahman, and nowadays we have some AI based methods which are able to uh, design music and sound for us, films and games and podcast, voice cloning. This is also one of the very important, and this is also being used by in some by some of the since in an unethical way, cloning the voice of your child, and they may just ask for some bribe, accent conversion. So uh, there are a lot of uh, generative models, which are basically used for the voice modifications, voice generation, and all. Audio restoration, accessibility. We can also just, in a similar way, we used to enhance the image using SR-GAN. We can also enhance the voice that has been degraded. So, for example, because of some reasons we are not able to capture good quality voice, then we can use generative AI based methods in order to improve the quality of the audio and recordings. So basically, how audio can be generated? Audio, we can have audio to audio transformation. We can change one form of audio to another. We can change female audio, male audio, and vice versa. We can have text to speech conversion. We can have speech to text conversion. There are a number of things that can be performed by generative models nowadays. So, for example, AI Music, OpenAI, Jukebox, Music LM, Google's Hackathon. So, each and every company has started to develop their own AI based tools for the commercial purpose. You can have your own. So no doubt, if we talk behind the architecture of any generative model, so nowadays we have started from MLP, that is multi-layer perceptron, that is being used for in the vanilla GAN. However, nowadays we are using transformer-based model to make our generative model more and more robust. So nowadays we are using transformer based architecture, and I hope we have also gone to the transformer models through the variational autoencoders in the previous sessions. There are some more popular models like Google's Music LM, Meta has developed AudioCraft, OpenAI has developed Jukebox. That can be that you can just go through and you can just explore that how these models are generating the synthetic voice or fake voice. So these are some of the tools I will provide you the PPT, so you can just explore in future, and you can just do some kinds of hands-on with these audio models that has been provided by some of the large companies. Now talking about the video generation, so what I have already discussed with you that video is just an extension of the image. So if you are able to generate images, then we can have the video by running those frames in the speed 16 frames per second. So you can have your own kind of video. You can just achieve the frame rate, but as a matter of fact, we will be needing high computational cost for that. We will be needing powerful GPUs in order to do so. You can also do kind of motion modeling. So for that, we have to predict future frames. So if you are able to predict future frames, then we can do motion modeling. We can mimic the motion of some of the other person. This is the power of AI nowadays. No doubt, with the evolution of the idea, we have some other approaches like text to video. We can just make video from image. We can do just motion transfer, movement from one source to another. That is called style copy. Nowadays, we actually used to see that we are copying the style of someone manually, but nowadays we have AI generated models which can perform the same task for you. So this is your homework. You can just go through these models and explore these. What is Sora? What is Google View? Pika, Luma AI, Adobe Firefly. So these are some of the model in video AI. So you can just explore these models and just have some knowledge that how these models are doing. And in future, no doubt, you can also have your model your own architecture. No doubt, what I was talking about Google View, I have also shown you some of the videos in the start of the session. And naturally, this Google View is also using diffusion based approach in order to generate video for you. So this basically diffusion based approach is used for basically developing some kind of artificial videos, motion transfers, style transfers, generating audio, and lots of applications that you can do. And no doubt, be ethically concerned that you have to use generative AI for ethical use only, because there are a lot of unethical uses. But be careful. You have to develop the model which are producing the output in the ethical way. Okay, thank you all of you. And if you have any questions, you can just ask me. These are the futures of this, and I will just share this PPT with you. You can just explore the various tools and techniques uh, that are given in this PPT for your future research work. Um, I do hope that you have got some idea of the diffusion models and other Gen AI based model like the generative adversarial network. You can use these models for your future research. I hope so. So if you have any questions in your mind, you can just ask me. Um, Otherwise, we can just end this session. Okay, so if you don't have any questions, then you may leave for the lunch. Um, Hopefully, next session will start at 2 p.m. So you may go for the lunch. Bye bye. Take care.
Yes, so next session will start at 2 p.m.